Alright, CNT120, Chapter 4, we're now looking on the section on Ethernet. Just a reminder, Ethernet really is down here at data link physical layer. I like to think of it as layer 2 and 1 together. I snap a NIC in my computer. The layer 2 function is the circuitry getting me access to the network. The physical layer is like the patch cable plugging into my NIC, or the antenna on my NIC connecting to a wireless network. So it really is kind of both of those layers in one. Alright, Ethernet 2, layer 2 standard, flexible, able to use a variety of different network media, copper, RF, fiber optic, and because of its kind of like good balance of being able to get the job done flexibly, it has come out on top as pretty much the default network standard, if you will. The majority of networks in the world are Ethernet using IP, okay, so it has kind of evolved into that. Here is our current Ethernet frame standard. We have these fields: preamble, destination address, source address, type field, and then the data. So if I take a look, here is our header fields. The preamble and start a frame delimiter, I can Wireshark all day long, and I'm usually not going to get them because those are really, those fields are really there to let the receiver know, hey, there's data coming. And to say this another way, your computer's sitting there and all of a sudden it starts getting a stream of ones and zeros. My computer needs to know, hey, what's important, what's not. So the preamble and start a frame delimiter are just that. It's trying to let the receiver know, hey, you got data coming and we need you to pay attention right now. So it really is a series that they talk about synchronizing the receiver clock. Absolutely. It's really a series of 10, 10, 10, 10, 10, 10, and the start a frame delimiter is literally after a 10, 10, 10, it goes 1, 1. And it's really like, okay, after this point right now, pay attention to anything coming beyond, because you'll find we now have the destination MAC address followed by the source MAC address and so forth. Okay? So the first real fields we end up seeing when we Wireshark are the destination MAC address, the address of the destination node or the destination MAC address, the source address, source MAC address where it came from, the type field, what upper layer protocol is in there, and then the data. And this would be the upper layer data. And we do even have a trailer, a frame check sequence, a little error check. That does not always show up on Wiresharks as well, just so you know. So if I take a look, here is, they give you some math here too. They give you some math on I almost forgot about this, with your header and your frame and your data. The data may contain 46 to 1500 bytes. We need a minimum of 64 bytes. That's your 18-byte frame plus 46 bytes of data, and a maximum of 1518. 18-byte frame plus your 1500 of data. That's your minimum and maximum Ethernet frame size. 64 bytes to 1518. They show you the breakdown of that and how we get those numbers. Here is a capture of a Ethernet frame from a network. And as you see, here's Ethernet, here's the destination address, source address, type field, and we're done. That's pretty much it. That's about all you normally get when you Wireshark. Well, with that said, let's do that. I have my Wireshark open. Let's just do a quick Wireshark. We're going to continue without saving. And again, I'll come out here. Maybe I'll load something new on my web page. So I'm generating some traffic. There we go. Excellent. I generated some new traffic. And I'm going to look at one of these chunks of data that I just sent or received. I'll grab one of these here. And if I look at this, let me close all my header fields. There's TCP, IP, Ethernet. Here we go. Ethernet. And you'll notice it says Ethernet 2, just like the book talked about right back here. Ethernet 2 is the current Ethernet standard. Okay, so you're going to see Ethernet 2 when you Wireshark that. Ethernet 2. Here's the destination address followed by the source address. Destination is a Cisco something, 84 CD, CB, blah, blah, blah. It's coming from a Dell device, 1866DA. So there's my destination MAC, followed by the source MAC, followed by the type field, IP version 4, and sure enough, there it is. IP version 4 is my next header. That would be the what's contained in it. So there, super quickly, is my Ethernet header and Ethernet header fields. And the book then says, okay, don't forget some legacy networking things. All right, so let's mention these super quickly. In legacy networks, CSMA-CD is how Ethernet got data on the network. And this was back in the bus topology Ethernet days. Bob Metcalf was the brain behind early Ethernet. And his concept, this actually is his concept drawing of a coax bus that we tap into, that we all send information back and forth across the ether, across this shared coax cable. And they did it first using this method here, where a little transceiver bolted around the coax cable and tapped into it, hence the name vampire tap. There's a little screw in here that has almost like a push pin on the end, if you will, that cut through the insulation, made contact with a copper conductor inside, and tapped into the network. And everybody used this central coax bus to ship data across. Eventually they upgraded and used T-connectors, coax T-connectors, that would twist lock onto the back of the NIC on your computer. And again, instead of being this bolt around transceiver, we're using the T connectors, but I still have this coax bus that we're sending data across. Well, because it was a shared environment, they needed to use carrier sense multiple access with collision detect to get data on the network. What it amounted to was your machine would listen to the wire, that's the carrier sense, to see is there any data on there. If there was, it waited. When there was no data, then it would send, and that's the multiple access. We're all sharing this coax bus together. And because we're all sharing this, eventually there would be a time when two of us try to send at once, so we needed a mechanism, collision detect, to know when a collision occurred, so we knew when to start over and resend our data. Hence, the carrier sense multiple access collision detect was the access method for these early coax bus networks. This is why they show this picture here, showing basically the T connectors connecting the coax together, or tapping into the coax bus. And when you sent, it literally went to everybody on the network. Hence, you needed to listen for anybody on the network, so you weren't trying to send at the same time anybody else was. And this was the kind of like the access protocol to do this. I would listen for activity. If I heard, I would wait. If I heard, I would wait. If I heard, I wait. Once I heard no traffic, I would send. And once I sent, I would listen for a collision. If I heard none, hey, I'm assuming it got there. If I heard a collision, then I would stop transmitting. A jam signal would go out, let everybody know there's a collision. We would all wait, and then we start all over and try to resend our data. That is how early Ethernet networks work. CSMA-CD access method worked on coax buses and early Ethernet networks. Make sure you do recognize this, because this is how Ethernet started. Once we moved away from coax buses, we would put a hub in the middle of the network and use twisted pair cabling. What you think of today is your patch cables, okay? Your patch cables would plug into a central hub here. Well, the hub is a layer 1 device. It has no smarts, if you will. So any data it received, any data it would receive in, it would repeat to everybody in the network. So it functioned very much the same as this. When data went on the network, it went to everybody. When data went on the network, it went to everybody. That's how the hub operated. So functionally, it worked no different, but admin-wise, I now have a device that each node plugs in individually. So if I have a problem with one node, it only affects that node. That's an advantage. I also have blinking link lights over these ports, so I know when people are connected or not connected. That's an advantage, okay? But functionally, it still works the same way of I send into the hub, it repeats to everybody. So again, I'm still using CSMA-CD. It wasn't until we moved on to the switch, a layer 2 device, that reads MAC addresses and stores MAC addresses, that we got away from this problem. Switches now are a layer 2 device. They read MAC addresses and store them. It actually builds a table in here on the switch of, hey, this MAC address is on this port, this MAC address is on this port, this MAC address is on this port, and so forth. Now the idea is when it sends data, when one goes to send data into the switch goes, oh, I know where that is, and send it only out that port. So that allows for a direct connection between 1 and 2. At the same time, 3 sends to 4. So we now have multiple connections going on at the same time and no collisions. That is a huge change. That gets us away from this old shared bus environment, shared hub environment. But it wasn't until we had a device with some smarts, like a switch, that could do this. So modern networks now aren't so much this as they are this right here, sending right to a node, sending right to a node. Okay? Well, when we talk legacy networking, they mention collision domain and broadcast domain. A collision domain is an area where collision can occur, and that happens when you have no devices of intelligence. Anytime I have hubs or anything like that connecting my network, a collision can occur and will occur. So if I actually have a hub here, this whole thing is a collision domain. Collisions can occur here. Meanwhile, when I have a switch environment, that is not a collision domain, because the switches are actually doing this right here, trying to make an individual connection between two nodes. So when I start adding layer 2 or higher devices, this eliminates that problem. Meanwhile, we also talk broadcast domains, an area where broadcast can travel. Well, I still need to worry about this. I don't worry about this so much anymore because everything is pretty much switched networks. So most of this problem has gone away. But I still do have the problem of broadcast domains. Anytime a protocol broadcasts, hence we go back here and look at my Wireshark from earlier, ARP is going to broadcast, okay? Anytime I have broadcasts like ARP, I need to contain them. And the only thing that's going to contain that is something with intelligence, usually something layer 3 or higher, layer 3 device or a VLAN. That's something you're eventually going to learn, so I'm throwing it out there. Routers, firewalls, and VLANs all create broadcast domains and contain them. They don't let them spread and spill, almost like containing a spill. You spill your grape juice on a table. I quick throw some paper towels down so it doesn't spread any further. That's what your broadcast domain, that's what your layer 3 devices and all are doing. So whenever I have something like a router, it's containing all the broadcasts to this network and not letting them spill out and go to this network. Same thing over here. This router port is keeping these broadcasts contained over here. So when I talk networking, when I talk Ethernet, I need to remember where Ethernet came from. Coax bus using CSMACD and hubs, again, CSMACD. It wasn't until we started adding switches that we started getting collision domains, or I should say getting rid of collisions and getting rid of that collision problem and adding a layer 3 device like a router or VLAN to control broadcasts. This is where we are now. So a lot of those things have gone away. A lot of those issues have gone away because of what we have designed and put in place. That is your collision domain and broadcast domain. We need to mention that when we talk Ethernet. We'll come back in the next section and talk about routers.